Welcome, this is Dr. Plague, and in this video I'll be making a homemade flash memory programmer. You will see me use this in quite a few future videos, so if any of those projects inspire you, then you'll definitely want to have one of these. This is a fairly easy project to make that most hobbyists could whip up in one afternoon. Now, this is something that you really don't need to make. You could just buy one. They're not too expensive. But if you have the parts laying around, it can be kind of a fun project to make. You should be able to get all the parts from DigiKey if needed. So let's give this a go. Now, this build is going to be broken up into several videos. And in today's video, I'll just be making the hardware for this programmer. Then, starting in part 2, I'll be working on developing the firmware. Ultimately, what we want in the end is to have some type of an app on a computer that will allow us to program a file into a memory chip, like this one that I made. This is the Plague Flash Programmer. I'll go ahead and open a COM port. You can see it connected to the programmer, and it found this flash memory device. So first, I'll check whether or not we have a blank part. And it is erased. I'll go ahead and select a file to program into the chip. And this is a Plague hex file, which will fill up the entire chip with data. So I'll go ahead and program that in. And you can see the progress bar moving as it programs. Then it'll read and verify the contents. And it's a success. Now I'll check again to make sure the chip is no longer blank. And you can see we have data at address 0. Now at first I was planning on making a custom PCB for this project, but then I discarded that idea. I want to get this video out as soon as possible so we can start some other fun projects. And if I designed a custom PCB, then I would need to explain that process and talk about how to use the software for designing PCBs, as I'm sure not everyone watching will know how to make custom PCBs. However, if you do know how to develop a custom PCB, then I would highly recommend that you do so, because it will make building the project so much easier. The way that I am going to make this programmer is to build it on a perf board like this one. And I'll be adding standoffs in the corners like this. That way there will be room under the board for all the wiring. Now, my design obviously is not the only way to make a programmer. You can certainly make improvements to it. And to be honest with you, I am not the neatest Plague. So this build will be kind of sloppy. However, this programmer will work and get the job done, and for me, that's the most important part. The microcontroller that I will be using for this project will be the ATmega 1284, which has 128K of flash, 16K of RAM, and 32 GPIO lines. The reason I chose this one is primarily due to the large number of GPIO compared to most microcontrollers. There's no reason you can't use another microcontroller, but then you'll be on your own designing the interfacing and firmware. So, what am I going to use these 32 GPIO lines for? Well, I'll need 2 of them to communicate to an external computer for sending and receiving data and files. And I'll just use a serial UART with an FTDI USB cable connected to a computer. Then I'll need 8 data lines to connect to the flash chip. I'll need 3 control lines for the flash chip, which are chip enable, output enable, and write enable. This leaves us with 19 GPIO lines to connect to the address lines of a flash chip. That'll allow us to access and program up to 512K of flash data. And having all these GPIO lines will eliminate the need for any I/O expanders. The flash chips that I'll be programming on this programmer are the Microchip SST39SF series of chips, although we won't be limited to just those. Those come in 128, 256, and 512K varieties, which just happens to match the number of free GPIO lines that we have on the chosen microcontroller. We could possibly program other chips as well, and we could either design or purchase an adapter for other packages or pinouts, such as this here adapter board for J-leaded parts. We'll deal with adding capability for programming other parts in another video. So this is going to be a very simple design, and I'll give you a high-level overview here. We're going to have our microcontroller, and this will be our flash memory chip that we plan on programming. I'll actually be installing a ZIF socket so it is easy to insert and remove the flash chip. And of course, I want to add some power and ground to these. I'll be connecting 19 address lines from the microcontroller to the flash chip, which will be A0 through A18. And this thick line represents a bus of 19 separate address lines. These will be coming from the GPIO pins of the microcontroller. Then I'll have 8 data lines coming from the GPIO pins to D0 through D7. Then we'll have the 3 control lines, and of course they will all come from the GPIO pins. And these will control the write enable, output enable, and chip enable of the flash chip. Then we'll have a couple lines to communicate with a PC, transmit and receive, and I'll have those going through a couple of buffers. These buffers are optional, but can help protect from unwanted voltages. And these will go to the FTDI connector, receive and transmit. Now, since I'm using serial UART, I'll want to connect a crystal to the microcontroller to ensure stability for the timing of the communications. And I'll add a couple capacitors to ground. Something else I want is a pull-up resistor to the reset line to ensure no resets in a noisy environment. And let's just add a switch into here so we can manually reset the microcontroller. And I'll send that through a resistor to limit any peak currents. I'll choose 10K for the pull-up and 330 ohm for the series switch resistor. So now let's look at the full schematic. You can see I'm using a 20 MHz crystal with 20 puff capacitors. These could be adjusted if needed. I've added a programming header here. This is for programming the firmware into the Mega 1284. Of course, I have the reset switch and resistors that I mentioned. You can see that I have a couple LEDs here. These will indicate when we have power to both the Mega 1284 and the FTDI connector. When using this programmer, we need to ensure that both LEDs are lit up before communicating with it. Down here we have the buffers that I mentioned, and for more information about the purpose of these, you can check out my video on protecting AVRs from an FTDI cable. I'll leave a link in the description. For the buffers, you could use 7407s or 7414s. But in my video on protecting AVRs from the FTDI, I found some other SOT23-5 surface mount parts from DigiKey that I said I would purchase. I'll mention the part numbers in the video description. So, to insert these parts into a breadboard or dip socket, we can use these adapter boards that I bought from DigiKey. They come with a PCB adapter board and header pins to solder to it. These are actually designed for inverters, but if we ignore the dot on the output here, this is still the symbol for a buffer. Power goes here and ground goes here. These 2 pins are no connects. And if we turn the board over, you can see that we have a spot to solder on the chip. And we can also add a bypass capacitor for power. Nice! Here it is after soldering the parts on. Now we just need to add the header pins. I'll use these here alignment spacers that I got from some other adapter boards. You could just use a breadboard to do this too, but you might risk melting the breadboard with the heat from the soldering, so that's why I use these alignment spacers. So I'll just add in the header pins, and I'll place the PCB on top of that. And here it is, all soldered up. Sweet! Now, over here is the FTDI connector, which connects to the serial transmit and receive pins on the Mega 1284. And here we have the ZIF socket for the flash memory chip. You'll notice that I added a couple pull-ups and one pull-down resistor to the control lines. If we look at the data sheet for the flash chip, we can see that if we force the output enable low, chip enable high, or write enable high, it can prevent inadvertent writes during power up or power down. So I've done all three. And all the data, address, and control lines of the flash chip are connected to the Mega 1284 over here. You can see I've added 0.1 mic caps to all the power pins of the micro and the flash chip. And talking about power, I am using a Murata OKI-78SR-5 switched mode regulator to supply the 5 volts. You can also use a common 7805 regulator. The regulator that I am using comes in 2 packages, one that is vertically and one that is horizontally mounted. I am using the horizontally mounted package, and with this you need to be a little careful because the pinout represents bending the 7805 over in a forward direction, not a backward direction like you would normally bend it in order to connect to a heatsink. Because of this, the pinout is backwards from what you would think. So this side would be the input and this side is the output. And of course, the center is still ground. But if we rotate the part 180 degrees, then we have the input, ground, and output. Now, I'm going to add 10 microfarad caps to both the input and output of this regulator, and we need to make sure the input cap can handle the highest input voltage. So I chose a 50 volt cap. As an easy method to protect from reverse polarity from the input voltage, I'm just going to add a diode in series like this. The input voltage should be plenty high enough to do this. A 1N5819 would work fine, since it handles up to 40 volts in reverse polarity. Unfortunately, I've only got these 5817s, which can only handle up to 20 volts. Therefore, I'll just use the common 1N4148, which will work fine since this programmer will be a fairly low current device. Now, for the power connector, I'll just use one of these terminal blocks with screws. This will allow for easy connection to a bench power supply, and if we want, we can use a pigtail connector like this to connect a standard wall wart power supply to it. You will notice that I specify 8 through 35 volts on the input. The switched mode regulator will handle 7 through 36 volts. So, to account for the diode drop, I spec'd 8 volts for the minimum. And since most 7805s will have a maximum of 35 volts, I spec'd that for the maximum. Although technically my design can handle up to 36 volts, and a little higher due to the diode drop. Now, one thing you could add is maybe some ESD protection, such as TVS diodes on any of the exposed lines. But the way I look at it, the flash chip will be unprotected anyway, at least until it is inserted, so I'll need to treat that with extra caution anyway. And since this programmer is only meant for development purposes, I'll just make sure that I'm properly grounded when touching it. I'll usually use either a wrist or ankle grounding strap. So, like I mentioned, I'll be building this on a perf board, but you could always just build it on a standard breadboard, kind of like this here. It does work, but you may have some issues with maintaining good connections, so I would only do this for testing before building a more permanent version. Also, I wouldn't recommend sticking these ZIF sockets into a breadboard, since the pins can kind of move around when opening and closing the socket. This can mess with the breadboard connections. One thing I do want to show you is that the switched mode regulator can give off some radiated interference. If we use an H-field probe and look at the emissions on a spectrum analyzer, we can see some frequencies of around 507 kHz, and all the harmonics above that. You can see these peaks go away when I turn the power off, so I'm fairly certain they are coming from the regulator. And if we look at the data sheet for the regulator, we can see that the switching frequency is in fact 500 kHz. Now, this radiation isn't too bad, but out of an abundance of caution, I'll try to place the regulator in a corner on the board and not right up next to the microcontroller. The interference probably won't be enough to bother the microcontroller, but at least I'll sleep better at night knowing I'm leaving a little space between the microcontroller and regulator. A half an inch or so should be fine. What you're looking at here is just a sample placement of all the parts on the top of the board. They are not soldered in. I just wanted to see where they could all fit. And notice that I added sockets for the microcontroller and buffers. This will make it easier to replace them if needed. Also, notice that I'm using a right angle header for the FTDI connector. You can use a normal vertical header if desired. Now let's go over to the bench and actually build this thing up. So I'll start by soldering on the socket for the microcontroller. And I apologize for the bad camera angle. It makes it hard to see what I'm soldering. It would be nice if my stereo microscope had a mount for a camera, but unfortunately it doesn't. Next, I'll solder on the sockets for the buffers. Then I'll add the FTDI connector. Now, I'm going to put the FTDI connector into the FTDI socket so I can add some cyanoacrylate to it, otherwise known as superglue. Since the pads on this perf board can easily rip off, I want to glue on any part that can be easily pried off during normal usage. And since we'll be connecting and disconnecting the FTDI to this header on a regular basis, I'll glue it on. Then I'll just hold it into place until it dries, and then solder it. Next, I'll add some glue to the programming header and solder that on. Let's take this switch and maybe the regulator. Now for the regulator, I'm going to use these surface mount 10 microfarad 50 volt capacitors and solder them on the back directly to the leads right here. This just saves some room on the top of the board. Then I'll solder the switch on. Now I'll add some super glue to the power connector and get that soldered into place. Let's take the ZIF socket and solder that on. Now I'll add the diode on the back and use the leads to reach the connection points between the power connector and regulator. Then I'll add a ground wire between the ground pins of the power connector and the regulator. And now the regulator is wired up to the power connector. Let's test it out. I'll use these jumper wires to connect the bench power supply to the board. Notice that each one is a different length. This will help ensure that they don't short out the leads to the power supply. So I'll screw those in. First, I'll apply 9 volts in. And I'm getting 4.99 volts out of the regulator. They cheated me 10 millivolts. Oh well, close enough. Still within tolerance. Let's try the maximum channel voltage of this power supply, 33 volts. And now I get 4.992 volts of output. So that's working fine. I want to solder these 0805 surface mount 0.1 microfarad caps to the back between these pins right here. But they don't quite fit since I already added solder. I could just solder them beside the pins, but instead I'll just desolder those pins and add the caps in with fresh solder. And there we go. Close enough. Now let's get these resistors in for the reset line. And I'll just bend the leads to the locations that I want to solder them to. I'll also add this ground wire to the switch. And there we go. Now I'll add the power to the microcontroller with these wires. Like this. And I'll take the crystal and solder that in place. I want to add the crystal capacitors here and here, and then I'll add a little wire to ground in between them. Okay, let's get the current limiting resistors along with the LEDs and bend the leads into place. Then solder them. Next, let's test out the LEDs to make sure they work correctly. I'll connect up the power supply and apply 9 volts, and you can see the red LED lights up. Then I'll connect the FTDI cable from the PC to the board, and the green LED lights up. Perfect. Next, I just added all the wires from the microcontroller to the programming header. By the way, the wire I am using is 30 gauge. I bought this 656-foot Adafruit spool from DigiKey for only $7.50. I'll leave the part number in the video description. Now we have everything installed to be able to test out the connection of the programmer to the microcontroller. So I'll pop in the microcontroller and add the power wires. Then I'll connect up the programmer and connect it to the PC. Next, I'll power up the board. Now I'll go to Device Programming in Atmos Studio and select the programmer, then see if we can read the device signature. And that works. Now let's set the fuses. I'll change the brownout level to 4.3 volts, disable JTAG, disable the clock divide by 8, and select the full swing crystal oscillator. And I'll program the fuses to these new settings. Then let's check the device signature one last time to make sure it works. And bingo, we're set to go. Now I'll power it down and disconnect the programmer and also remove the microcontroller for the rest of the assembly. I'll place the flash chip's 0.1 microfarad cap back here and use the leads to span between power and ground. I've now soldered that in, plus more power and ground wires. By the way, I'm not showing any more of the actual soldering because the camera angle doesn't do it any justice. I'll just show the finished soldered connections. Here I have soldered all the connections between port A of the microcontroller and the ZIF socket. Next are the port D connections from the microcontroller and the ZIF socket. And the port C connections. And finally, the port B connections. Wow, that's a lot of wires. A bit of a mess. I hope I didn't make any mistakes. Okay, let's get these final resistors added in. And here they are, all bent into place and soldered up. And finally, we'll get the buffers all wired up. Whew, glad that's all done. Let's add some markings on this board to indicate the polarity of the power connector, plus and minus, and the negative side of the FTDI connector. Let's also indicate which way the connector goes for the programming header. Now let's add in the microcontroller and the two buffers. And to protect all the wiring I did, I'll just screw on another board underneath the main board and add some more standoffs. And there we go. The programmer is all made up and ready to be programmed. Now, we could 3D print a nice enclosure for this, but I'll forego that for now. That was a lot of work, so let's give this a quick test. I'm going to use the code from one of my previous videos titled Floating Point with Printf and Scanf on AVRs. So I'll go ahead and program that into the Mega 1284. And that programmed fine. So I'll power it down and disconnect the ICE programmer. Lastly, we'll test out the UART functionality by connecting the FTDI cable and starting up TerraTerm. I'll set the baud rate to 115.2. Then I'll apply power and we can see the output from the microcontroller just fine. And, of course, the microcontroller sees the input just fine. So, this was a success. Well, that's all I have for part 1. In part 2, we'll start writing some code for this thing and see if we can read and write to a flash memory chip. If you liked this video, please give it a thumbs up. And I'll see you next time, right here on Dr. Plague.